All right. Hello, everyone, and welcome to, I guess this is the first episode of Doesn't Grasp. Doesn't Grasp is going to be a sort of robotics, AI, foundation modeling focused podcast where we talk with a variety of interesting folks from research and the industry to learn a bit more about what's actually going on in the robotics world outside of the viral tweets on Twitter, which seems to be how a lot of people are getting their news these days. So for this inaugural episode, we have Mr. Dane Kouttron. Dane is a man of many, many talents. He also goes by the name Transistor Man on the internet. And if you really dig, he's got quite a bit of footprint. So Dane, introduce yourself a bit.
Sure. So I've tackled a lot of things, ranging from amateur robotics to getting your local fission reactor up and running. My background is a lot of hardwares and controls things, but most of those have ended up coalescing into making robots do things in a somewhat useful way. One of the more interesting things I've been trying to tackle is getting machines to accurately paint in like an artistic fashion. It's a curiosity of mine that has spanned almost 7 years at this point, and I would love to delve in more in the world of robots, art, and learning more about how painting even works in the first place.
Yeah. So this is an interesting topic, right? Well, so while getting your robot to do fine art is perhaps of suspicious utility in the end, I think it's a highly representative task for a lot of useful things. It involves a lot of force feedback. Painting is force mode. It involves the data collection is especially interesting if you're going for an end-to-end approach, as the guy doing the teleoperation also needs to know to paint. So yeah, tell us a little bit more about how all this got started.
Is a fantastic question. So this started from a robot art competition. Yes, there is a robot art competition. So the beginning was simple. It was someone just really wanted to see what robots could do. I'll pull up his name in a bit, but formed a competition. It was nominally global, and the goal was pretty simple: don't do pointillism. That's not painting, right? So there was no bounds for what is a robot for this competition. So could be a Roomba with a paintbrush taped to it, or it could be some elaborate Kuka in a Columbia laboratory. But the judging was part by a panel and part by popular vote. So you had to get something that actually got the attention of a large group of people, but also passed mechanical muster. And this competition evolved pre-generative AI imagery era. So the early robot art was what it sounded like. It was, how does this even work? It starts off with, I can paint, right? I painted a wall. How hard could it possibly be to do something more complicated on the wall? It's suboptimal. So the first machine that I started with, I saw this competition. I had access to machines, but I wanted my own. And the best way to get access to your own machine is to not use a brand new one, but to use something legacy. Right next to me is a Yakusawa robot, rebranded Adept. But there's further industrial machines that have found new homes. One of which is next to me. It's a Dainichi Kiko Japanese robot. Again, undocumented. Somehow ended up in the States, but it's large and it's 3 axes, and it was kind of the first pass at what is art. So there's a lot of layers to it, specifically layers. How do you discern the background, the foreground, and the subject from an existing image, which still is a difficult problem to solve, right? We do it without an issue now, but it's difficult to discern for complex subject matter. So the concept of let me get a robot to paint something is challenging, right? From managing the actual paint load on a brush, to managing the force requirements, to compensating for things like how the canvas changes as it's being weighted down by more and more goop. How does the paint that you've previously applied interact with the paint that is now applied? Do you need to keep it all moist during the entire time of painting, or can you get away with some sort of curing agent? There's a lot of challenges to try to make a good painting. Making a bad painting is really easy, though. These machines are wonderful at expediently generating trash. But it's been an interesting challenge to try to bring some of these elderly robots into the new age with more modern control systems and way more modern processing.
Yeah. Quite frankly, I mean, if you told me to paint a masterpiece, the idea of separating the layers, managing the canvas sag, that's all really skilled, right? And I think when the first time you built this thing, it was pre-foundation model. So all of the motion planning algorithms, all of the controls were based on more traditional algorithms.
Correct. Yeah. So it's exciting to see how much has changed over a ridiculously short period of time. Most of the East Coast approaches to robotics are physics based, right? So that's you have you know your robot's dimensions to a T. You know its mechanics to a T. You can derive its kinematics, and from those kinematics, you can have a position-based mode that is like almost absolute. That's great for pick and place. That's great for, put capacitor here. However, it's not ideal for activities where you have like a less deterministic state, right? The paintbrush doesn't necessarily always need to end up at the exact same position. The dynamics of the machine are not actually necessarily totally necessary to the level that is required. So the first pass was exactly that. It was a kinematic model, a real-time operating system that's used for CNC activities was used because that's what really existed in the open source realm. Since then, since like 6 years ago, we went from these very static kinematic models to throw a bunch of training data at it. Who cares? Just throw more training data. Oh, it's wrong. How about more training data? And that's really the wild path forward because it does scale. It does solve a lot of very difficult problems that were otherwise very, very energy intensive to solve.
Yeah, and I think that this is one of the, I would say, undisputed successes of machine learning, right? Manipulation was incredibly laborious to do before we had machine learning. You had to have a team of grad students, carefully craft the models, carefully craft the rules, and then have it all probably not work outside of the paper. But we've hit a point where I would argue that the data-driven approach, while it does require collecting data, is still a heck of a lot easier to deal with than the old manual approaches. Like if you actually dealt with the manual approaches, they were not fun they were not fun.
It's terrible. And one of the parts that's less talked about for the manual approaches is if you are wrong, right? So if you define your system's kinematics slightly incorrectly because the paperwork you found detailing some of the robot specs was not quite accurate. The things like the inflection points for joint motion go off the rails because the acceleration bounds are no longer really accurate. The points of inflection not where they're supposed to be, and you get these, especially for non-Cartesian robots, complete goofy nonsense. Right? The problem is if you can't draw a box with a kinematic model, something's terribly wrong, and that's super easy to do for a Scara, where each of the axes is a theta, right? So any error in that initial model immediately propagates to everything else. And it's not easy to discern immediately. So moving over to like a visual model approach or a follower leader approach for training is a huge increase because all of that error is folded back into vision data. Now, is that vision data sufficient to do the job well?
Yeah, so I guess that's some really cool insight. With the ML methods, you don't need to know what the robot is. You go collect things like the encoder angles, and the model learns the kinematics, which is pretty neat. It's as you say, it's a traditional problem to get the link lengths wrong and then wind up with some infinite speed near a singularity on your robot, which is a miserable experience. And it's really terrifying, right? Like the entire robot will just whirl around in space at infinity speed, and there's a lot of mass.
It's only slightly terrifying, and the robots, like when they're desktop size and cute, it's fine. When they, are the first model robot that ever mortally wounded a man, it's terrifying, right? These things can be big, and those bounds can be, a lot. Now, I think that the question right now is, are we there in terms of the visual information that's stored? Because things like force for painting is very important, but is it fully captured in visual data? That's I think one of the questions going forward.
Right. That's one of the interesting things that I think the industry as a whole is debating. We all agree that we need to capture force in some way. It's really important for painting is actually a pretty legitimate one. If you want to build a robot to do like body work on your car or something, that's a real use case, and you actually do need the force. There's obviously like deformable objects, food, sacks full of returned clothes are like a common one. It's like a popular. I think it's a made up use case, but a lot of people are working on it. That they think Amazon has to process, billions of return pants every year, and it's a huge problem.
Let's pump the brakes. Everyone who processes soft things, it has some way to cheat, right? You either detune your machine so that it reaches through the soft thing and you pray that the visual data is there to show that you've reached through it, or you're doing some elaborate trick because the visual data for training for a soft object is difficult.
Yeah, right. So I think the way most people handle soft things is they expect the thing to just squash, and like that's how we do it. The thing is soft enough that the position becomes force. But this is like a pretty poor approach if you can't squish the object. Like, I don't know, if you're trying to pick and place live hamsters for some reason. I don't know why you would want to do this, but it's like a reasonable thing. Hamsters are deformable, but you can't just squeeze them until they deform. You get a pretty unhappy hamster.
Yeah, and that's part of one of the big things right now is the visual language models exist. Not enough people know how they work on the inside, so it's difficult to patch in external force data directly. Right, that's the goal. The goal is the visual model can take in that visual data, but also feed in synchronous sensor data that can be used for training. But that part isn't fully solved to my knowledge, or rather, it's not solved off the shelf.
Yeah, I quite frankly, I don't understand why a lot of the existing VLMs, they like collect force during training, then choose to omit it like they collect force during data collection, but then omit the force during training, which is kind of silly. But are there like interesting visual tricks that you could use as a proxy for force?
So that's the next part is, can you make your manipulator so squishy that you can see its deformation and then kind of squint your way into having a force vector, right? So that's the path that exists right now. And that is, you use a deformable gripper, you watch the deformation of the gripper with a localized camera, and then you pray to the machine gods that information is captured in that very low resolution image that's being used to train the model, right? Let's acknowledge that at this present moment in 2026, our visual models are trained at sub YouTube resolution. Let's just
240p, 480p if we really scrimped,
which is effectively like old person cataracts vision, right? So you are training something that has the ability to see of either a newborn or an old born person, and that's where we are. And that image space is bounded by what we can dump in for graphics resources at the moment. I mean, that's really what the bound is. I mean, the models are, okay, I guess what really defines that 240 pixel image?
I think it's just choice, right? Like it's mostly bound by compute resources and the necessity that the model does eventually have to run in real time. Like, even if we ignore the part where the model fits inside the robot, the model does need to run in real time on something. Like,
Correct.
There needs to exist a computer where the model can run at like 10 hertz if we have really low standards, 25 hertz if we have like medium high standards. We all want 100 hertz, but that's just not possible right now.
And moving to something like 720p would push that to what?
What a dream!
0.1 hertz.
So it's bad, right? The models are full attention based on the input. So if you double the linear resolution of the image, you quadruple the pixel count and increase the compute load by a factor of 16. There are very few industries where the level of fuck rises as the fourth power of the resolution. But here we go.
It is bad. Like, you only get that with weird magnetic field strength.
1080p is not achievable right now. Nowhere close. And I think this is in general a problem which plagues the entire like dense video AI industry, right? Like, the video generation guys quickly ran into this last year, that they have these beautiful models, but they would generate 1080p videos at the rate of 5 seconds per hour, consuming measurable amounts of server depreciation and electricity. Like, the number of joules going into that computer generating those frames was measurable.
Yeah, and it's not clear there's a path forward to get there. Like, it's either GPU scales by a factor of 14 times better, or something else happens in the background, right?
Yeah, it is hard. Like, maybe the answer is just a lot more GPUs. Unlike 10 years ago, we can't really believe in the future for compute anymore. It is what you got. It is what you got. There's no more Dennard scaling. So, segueing a little, you mentioned these industrial robots earlier, and I think this is a enlightening discussion for our viewers who have not had to deal with a traditional industrial robot before. Can you try to elucidate to our audience just how miserable it is to work on industrial robotics?
We're going to start with how amazing they are and then end up with where they actually are. So these machines were born for a specific task, right? They were born not to be cobots. right? Cobots are happy to not squish the person. These were born to do a task forever or for a comically long time, right? So there are these like, huge Kuka-esque robots painting cars for a decade, which is a ridiculously long time for that activity. And painting a car is something that can change vehicle to vehicle dependent. They have huge spray guns, but they are in a messy environment that's full of noise, but they're huge, they're repeatable, and they are cheap in the surplus market. They start as very expensive, but the moment that a new wave of them exists, you end up with this little fella. They're never little, are they? This little fella who is got the resolution and positional accuracy that you could not get with a UR5. However, to get that, you are a little bit stuck either using the legacy vendor's control system or building your own. And the building your own route, while it sounds spooky, is so much more trivial than imaginable, right? So when this was born in the early 2000s, sensorless or censored field effect, field-oriented control schemes for brushless motors was, a PhD thesis topic, right? They existed, but they were mysterious. And now we have quad rotors that have an update rate of like 200 hertz and can barrel down a tube at like Mach 0.1, 70 miles an hour. So we have the tech. It is no reason to use the ancient control schemes, especially if that gives us an advantage, right? A robot from this era has these adorable, this is specific to this machine, servo drive. So they're not enormous, but there's one of each per axis, and which this has 6 axes, so it starts to stack up pretty quick. Because they're legacy, they also become expensive. The robot without the controller is a comically budget-friendly item, especially for the enterprising researcher, right? It's basically free, right? You have the machine, which the mechanics haven't changed. These are harmonic drives that are gorgeous. They have brushless motors that are integrated in the axes. They have ridiculously good encoders. This knocks the socks off of the UR5 in mechanical specs, but to get there, you need something to drive it. One of the big, if you read any of the recent model papers, one of the big grumbles is what exists between the beautiful industrial robot that could, punch through the desk and the goofy little academic robot, right? So there's the universal robots do exist, but they have some drawbacks, right? 20 hertz of an update rate is not great, right? Especially now, the UR5s, which are super common, are getting up there on their age, but they are such an established, factor that they don't really change that much. So a 20 hertz update rate is rough. Moving to 100 hertz or more is super feasible. So one of the routes forward is it's called the Stumble project, STMBL, and I've contributed to that project. So we make these cutesy little DIN rail mounted servo drives that operate off of an external DC supply. So suddenly you've gone from 6x of this to 6x of this, and the space constraints suddenly become small. These machines are not terribly high wattage. Getting to 100, if not 200 hertz of update is not even unheard of, right? We have network protocols that happily can pump data that fast. We're no longer stuck in these goofy, what is this connector? Seriously, what is this? Who knows? Who cares? We're now at the point where it's spooling up a servo drive is trivial. Making a rough kinematic model that a model can eventually fold back in is no longer thesis level. This is something that you grab off of GitHub. So reusing these machines, which are mechanically, let's be straightforward, nothing has changed mechanically, right? We haven't gotten gearboxes that are suddenly like an order of magnitude better. If anything, they've gotten worse, right? We're getting.
I think they've gotten worse in the quest for lower cost.
In the quest for lower cost, they've gotten worse. So these goofy gadgets are sitting there abandoned, right, collecting dust, while they contain these gorgeous harmonic gear drives, these like beautiful Japanese motors, and are happy to put the effort in to be used for in this case robot art. Am I just opening up a retirement community for aging robots? It's a good question, but I'm super happy to put these to use, especially for the tasks of painting at scale, right? This is still nominally portable. Is it as lightweight as one of the universal robotics? No. But is it going to melt down like a Dynamixel based goofy contraption? No. We've all burned down the Dynamixel.
Yeah, We're
If
all
you
quite familiar with the ST-3215s just catching
if
fire.
you try to get a Dynamixel to just hold its state and fight against gravity, it will cook itself. That's not okay. That's not robot. That's just an advanced toaster, right? I think this is really like an interesting path, especially for a route forward for research.
Yeah, I sort of tend to agree, and I think you're really right. The difference between something built 30 years ago and something now is just the electronics and the software. Like, I literally don't think the mechanical design has changed since harmonic drives were invented. It's a pretty constant thing, and honestly, even for modern robots, the software is pretty bad, right? I had a LBR Iwa for a while, which is a $55,000 robot from Kuka that was current gen until very recently. The controller was a dual core 2 duo with 2 GB of RAM running Windows 7.
Oh,
And the programming interface was Java. It was like Java 1.4 or something. It was very bad. It was very bad.
I think that we're all waiting for China to make us the super budget happy brand new version of this. But that is not happening. That has not happened yet. And that still is going to take a while to happen, right? We all want China to make me, equivalent to this for super, reasonable price. But that is a tall ask right now.
It is a tall ask, and there's a lot of stuff that goes in a robot like that. But at the same time, there's also, to your point, a million of them were once built.
Correct.
And are just around. There's like plenty of robots to go around for the next foreseeable future for research and even deployment. Like the factories, they like go through their hardware once every 10 years, and that hardware all goes somewhere.
Correct. And it's not like you're limited to one size. If you're suddenly like, I want my 10 kilogram lift robot, like 10 kilograms. Honey, you can get 100 if you want. And that's like it's not going to be moving from the 20 kilogram robot to the 100 kilogram lift robot is the same price. They get cheaper the bigger they get because no one wants to deal with a big robot. So suddenly you can get your 100 kilogram lift robot and really make some bad decisions.
I've always wanted to build a teleoperated mech, and it feels like something that used to handle car doors would be the perfect machine for this.
You go to the auction, and I'm pretty sure they can get the 4-pack of these things for not much more than the single unit.
Arms and legs. Continuing the dream that the legs and arms are just the same design. We make no distinction here. Speaking of teleoperation, I think this is an interesting one, right? Teleoperation is tricky the bigger the robot gets, and right now most of the research is being done on these very standard 700 millimeter long 0.5 kilogram payload machines. But obviously in industry, like, that's not the only robot. The industry uses robots. Like the thing behind you is a small robot by industrial standards. It's tiny.
Yeah,
real industrial robots are literally 5 to 10 times bigger than that, and they're used everywhere. But I think there's like some reasonable argument that eventually we would like to bring modern machine learning to these industrial settings. And in order to do that, we need a way to control the robot for data collection. How do you do that?
The real question is, can the model compensate for the super duper differences in kinematics, right? None of these scale mechanically 1-to-1, right? They don't just make the size medium, the size large, the size extra large, and the size Walmart, right? They all are mechanically different in terms of linkage lengths because they're trying to solve different problems. They don't scale 1-to-1. So the goal is, can the model fold that back in? And the answer is not yet, right? I feel like there has to be some nominal overriding physics constraint, right? If that's just like, here's the rough configuration and then fold the model into that. The concept of the model can operate any arm is, in my opinion, kind of not the route to take. You have some information, right?
That is an interesting question. Like, is it possible to build a model that can like zero shot an arm that it's never seen before at all? And I think I tend to agree the answer is probably it's a bad idea.
I feel like it's what problem are you trying to solve, right? Is there ever a case where you're like, yeah, that thing that's over there, I don't want to give the model any information about it. I want it to wiggle around and thrash and destroy the gearboxes until it figures out what it is. No.
We call that reinforcement learning, is the process of flapping around until you find the right answer.
You have time and energy and attention resources. Put them to use, right? Give the model constraints of like, hey, buddy, you are this tall, you have this much of a reach. There's no reason why the model shouldn't be able to take that back in as feedback. But that's the problem right now, right? Taking in force data is still not really sorted or not really easily available for that training. Giving the model constraints in terms of its actual kinematic state, in terms of like its physical layout, not really always baked in, right? You'd imagine there'd be a standardized YAML file or a standardized JSON file to define, hey, here's what you're embodying right now. But that's not totally baked in yet.
No, it's in fact all hidden. The model knows nothing about the kinematics other than changing the inputs changes the output. And it, like, all of the kinematic learning is blind, which is kind of goofy. You're relying on the model to learn the forward kinematics of the robot when you know them.
In actuality, you don't rent an 18-wheeler to a 12-year-old, right? You're not like, here you go, like, best of luck, boys. And like,
yeah, like if you press the pedal, it goes forwards. But go figure this out yourself.
Levers, and who knows how the hell a transmission works. And the kinematics of driving an 18-wheeler that's articulated is totally different from a Suzuki Jimmy. They're very different vehicles.
He's driven a tricycle before, so we expect him to be able to do transfer learning to the 18-wheeler.
No one benefits from giving the child the keys to an 18-wheeler with no training. Right, that's what we're doing. The goal is like, yeah, it's got a learner's permit. It should be able to operate a space shuttle. No, we train people for things.
Yeah, this idea of like few shot, zero shot cross embodiment generalization is really, really quite silly. There's a finite number of embodiments, a very finite number of embodiments.
Zero shot,
especially relevant ones.
The zero shot approach sounds great because it's a wonderful anime title, but otherwise it is functionally useless. Like, you are never in a condition where you should be zero shotting like and waking up a machine.
Yeah, right. Like, presumably that machine, like, you're investing some sort of time and effort into the machine that like you could at least collect 10 hours of data.
Can you think of any example of when you want to blindly wake up a machine? Like,
it's basically hobbyists and researchers, right? They're like, I want to turn this shit on, but I'm too lazy to do anything.
Ian, let's go step back. A CNC. You're like, here, when I'm going to tell you what the bounds of the CNC are, it's a 3-axis. Let's say, good luck, machine me apart. No one wants that part. It's terrible. Like, in the best case, you didn't destroy the machine. I think that the zero-sided shot approach just sounds cute, but it is a functionally goofy idea.
Yeah, but it does bring up the question, right? If you can't zero shot it, you need some way to collect data. And the bigger the robot gets, the weirder the data collection gets. Like, are we actually gonna operate mech-sized robots that pick up car doors? Like, maybe the answer is yes.
I mean, that's the future we all want, right?
It is the future we all want. I've not seen someone do the like teleoperation foundation model loop for really big stuff yet. We're like mostly in the 200-gram range right now. Maybe a kilogram if you're ambitious, like a can of beans.
Just why? Why do you think that everyone's using the tiny baby robot? It's so much easier to fit like 20 of these that are like adorable size in a workshop than it is to house 20 monsters, right? So, however, and those monsters mechanically are large, so they take up space. But if like a new large Kuka is expensive, an elderly large Kuka is remarkably cheap.
Basically negative in price for the really big ones.
It is,
like, the man will pay you to take it away.
It's less than scrap value because it is just so obscenely large. And like, I think what might be really funny is there are hubs where, things are developed. SF, Boston, in part New York City. But this might be the case where the goofy places that have just zero real estate value become like mecha giants, right? Will Ohio be the centerfold of like the robot mecha revolution? Just because they have warehouse space, they have infinite warehouse space.
Forget the data centers. We're going after robot centers. Like, it's just farms full of mechs, acres of mechs being remotely driven.
Like, it's just a bunch of teleop huge old Kukas ripping apart cars for scrap. I mean, that's the future that we want, right?
It is definitely the future, right?
Like,
you walk out, future. You walk outside and there's a 30-foot tall mech built out of used Kukas going and, like, I don't know, collecting the garbage. Instead of the garbage truck, we have the garbage mech.
I mean,
I'd love that future. Someone, someone's got to make it happen.
So, okay, right now the garbage truck is like a dude who has to run along the truck, maybe even drive it, and then like run beside. I want like 6 arms that can reach across the entire street, and they just pick up the garbage. Like the vehicle is moving at a constant speed, and the arms are so long that they're just like throwing it in the back of it. And it looks frightening, but everyone's like, I have not been stuck behind a garbage truck ever after that point, right?
I
These
really wonder whether, I'm surprised there isn't a startup already doing this. You feel like in this day of robotics is hot, there'd be some guy trying to replace the garbage truck with like a spider.
Man.
It's like a 4x scale model of Doc Ock from Spider-Man, but instead of like committing crime, he removes trash.
Again, this is the point of this podcast, is to get those folks out.
Yeah. If
I want
anyone's
trash moved ASAP. I mean, think about the recycling too. Like, it's just like throwing cans and like things into the back of the vehicle and just scootling along. I love it.
If anyone's listening, trash removal could use some disruption right now. I actually don't know. You're right. It is miserable and expensive to be like the garbage truck guy, and I think they like, it's really expensive to do residential trash removal. Like some guy needs to, like the truck needs to visit every house in the world once a week. That's a lot of work.
And if not more than once a week. And it's
like literal trash, right? Like out of all the things you don't worry about breaking, it's the trash.
Yeah,
it's
which is a
garbage.
Great option for robots without force control, right? They can just kind of crush the
crush the trash can and rely on its springiness.
Just throw it in the back. I mean, I'm gonna put that one down on a list of things to do. Giant robot garbage truck.
Back to the painting. We've gone some good ways, but I think going back to the painting, right? I think it's a very unique space because it definitely involves force control, and it's a bit of a binary problem too. You're either contacting or not contacting, and the range of contact in which things paint is really narrow. Like if you squish the paintbrush too much, stuff goes wrong. I guess you've done some work in like making this work in the past. What were the control schemes you used in the past, like traditional control schemes?
So you can cheat, right? So let's say that you are just painting a line, and in the purest sense, the Z difference in height defines the thickness of that patch. You can do differential imaging, where you paint a single line and you take the image before and after, and you determine, was I even on the canvas? If you were on the canvas, great. Was it just smashing through and making the widest line on Earth? Or was it just making a wisp? And that's an image, an overhead image, where the robot is not occluding it, so you have to move out of the way, specifically just to get the information for, is the width of that path significant? Right? Is it what I want? And do you know how much time that adds to the process? It's ludicrous. It works, right? You get an accurate ability to feed forward control the actual height of the brush, which defines the width of the painting. But is it worth it on the time? By the time you finish the thing, that all of the acrylic paint is turned to dust and there's nothing left.
It really brings me back to the days of traditional computer vision, where this was how we ran. We like took the difference between two images, did the edge detection, did some like random C++ script to find the width of the line written by some grad student, and the whole thing was a house of cards. And the instant the lights changed or the canvas moved 2 inches to the left, it was all over, and you had to start from scratch.
Exactly.
Do you have plans to introduce more machine learning into the robot art pipeline?
So that's where it gets exciting. So I think that one of the big things that needs to really be fully exsolved is like a kinematically agnostic jello, right? And that is, how do you capture someone who's doing something delicate without making it very, very difficult for them to do their task, right? I mean, in the ideal case, you could just get cutesy accelerometer, IMU, attach it to a paintbrush, and that's great. No. No,
you get the wrong answer. You get mostly IMU drift.
That gets you the wrong answer and doesn't give you any information about the position of any of the axes to get there. It's just prayers, right? And that's not what you want. So you end up fundamentally needing a leader, which demonstrates what were the positions taken for that. However, conventionally now, the leader has to have a geometric proportion that's equal or like ratiometrically equal to the arm. Right. So for this case, that leader is going to look really weird because and that's not how a human arm's really routed. So suddenly now this person right, who's super skilled at calligraphy is now like doing these awkward gymnastics to try to pretend to be a machine doing it. And that's not what anyone wants. The goal is pretty simple. I want to grab a bunch of art people and just figure out how they work. And part of that is give me a good position estimation of how do you do that. And that's, that's something that needs to get resolved. That's agnostic to the robot's dimensions, right?
Yeah, I think that is it's a problem that I think if you are a practitioner in the field you run into. The leader geometry isn't great, and even if you didn't have to teleoperate a robot, the fact that you're constrained to the kinematics of the leader is really unpleasant. Like, especially if the task is end effector angle sensitive, the way that leader wrists work is usually different from the way human wrists work. And even if it's like a parallel 3-off wrist, if you're grabbing the like handle or whatever, it still doesn't really match your wrists anymore. Right. And now think about trying to do fine art or like write. Like, I challenge you, if you have a robot, to grab the leader and like write with it. You will find it's perhaps much more challenging than you thought it was.
Yeah, and there's some routes forward. Like Stanford is doing a bunch of interesting research where there is just camera on wrist, camera on
good old UMI. Yeah,
and I think that it looks really cool. It is really difficult to duplicate, right? I think a lot of people are trying to duplicate it right now, and I think it's
so many of them.
I think it's still very like fiddly in terms of actually being able to fully duplicate it. Believe me, not having to build a Jello to just comically map this goofy gadget to an art person who has no idea why they're there, they're just doing some cute art with a robot attached to them, is a different story.
Yeah, I think UMI has seen a number of successes, and there's like a unreasonable number of people trying to sell you the grippers now, but I don't think it's good for fine accuracy. Like, I think their localization is good for a few millimeters, so it's fine for picking up donuts or whatever, where you can sort of miss and then just like squeeze really hard, but probably not so great for fine art or like installing fasteners. I don't know. Generalists, I think, claim that they were able to install fasteners using a model trained with UMI data, but I would also believe that they aggressively fine-tuned the fastener demo.
And it's likely they are it's a really talented bunch of people, but that's difficult. Like, we've all seen the video. It's really impressive, but
yeah, I've seen the fasteners in person, and they do in fact work. It is the same fastener over and over again. Like, there's a guy at the booth whose job it is to go remove the fastener.
Wonder what poor intern was stuck doing that.
Yeah, like, can you imagine being the trade show guy? Like, you have to be the inverse of the robot all day. I called them.
Have it undo the nut afterwards. They had to.
I don't think so. I think the resetting was done. Was done. Done by person. I need to go check my notes. Maybe it was autonomous. I think it is interesting. What I call these rogue modalities are getting popular. I don't know about you, but I get about what 1 or 2 egocentric video data vendors in my inbox a week now. And now I'm getting like guys who propose to increase the sales leads of my egocentric video. It's really we're like full turtles all the way down. The BD guy to sell the egocentric video he doesn't have to customer he doesn't have already exists. Like, the customers don't exist, the data doesn't exist, the robots don't really exist, but goddamn, the BD guy exists.
Well, so what I think is interesting, right? So you've got this particular realm of like, hello, I'd like to paint a painting, doesn't have the huge demand of like, I need to fold squishy used clothes. So it's a lot. I'm gonna say it's a little bit more pure. I feel like the challenge is it does have applications, especially to soft robotics, especially to like picking up soft things. But the goal is like purely, can I understand what painting is? Can I make it paint to a level of satisfaction that is at a similar level of a human operator? And then what can I learn from that process that could be folded back into things like dealing with squishy fabrics, dealing with squishy targets? I think that there's a huge amount of information to be that are there. There's a huge talent pool of people who can paint with acrylics. I haven't even touched things that are not acrylics because I don't have the freaking patience for whatever oil painting is, and got no time for that. But like, God forbid, watercolors. What is that? I don't have enough bit depth in my eyes to figure out what's going on there. So I think
acrylics are about all I can do, right? Like, the paints are pretty opaque.
Yes, exactly. I think it has a really cool option of folding that training back into things that are less painting, like, even if it's like decaling something, or just, dealing with things that deform like the paintbrush does.
Yeah, you could probably transfers neatly into spreading jam on toast. You could have an extremely expensive machine that makes peanut butter and jelly sandwiches.
Ooh, artisanal peanut butter and jelly that's like
Yeah, made by
got,
robot.
yes, it's got your local advertising information painted on the toast.
Man, there we go. The peanut butter and jelly is spread in the form of an ad or a scannable QR code.
Ads, like getting political ads that's just like black and white, but it's peanut butter and jelly.
No,
like vote for Biden 3030. Like, come on.
Subliminally advertises the latest campaigns in your lunch. Like, you see them every day.
But like, think of how good that painting of that peanut butter is going to be.
I do think it's a really interesting. I do think, hands on sandwiches aside, it is a really interesting research field, and I think there aren't enough people working on it, right? It's a really compact task. It doesn't require a huge robot or a ton of space. You know exactly what you want. Like, there's a very clear, like, the robot has painted this letter and it looks like something a human could do. And like, correct, even an 8-year-old could probably tell whether the handwriting was good or bad.
Yeah,
but it is really clear, surprisingly challenging. It is surprisingly challenging. I think it's much harder than what people are doing today.
Challenging is also like, that means that there's a lot of stuff to be dug out of here. There's a lot to learn from how this process works.
Yeah. I really do wonder whether that data would mix well into the existing more like rigid body pick and place task, right? If you like look at what the models are training on right now and you like really stand back, it's all still pick and place. Like, sometimes the pick and place follows some set of instructions, like maybe putting A onto B results in an assembly C. But fundamentally, the task is pick up rigid body and like put it on top of another rigid body, whether it's like busing, dishwasher, assembly, like basically everything except the ubiquitous folding shirts is a pick and place task. But humans do a lot more than pick and place, and I would argue like the most valuable like human laborers in the world do not do pick and place very much. Okay, it's like those non-P&P tasks are the ones that require real skill.
Okay, so I want a slight tangent. What are we doing about the one DOF gripper? Right, everything right now is trained off of like Mr. Pinchy.
Yeah, this is a big problem.
Okay, part of the reason is like there just isn't a hand, or okay, there are, but there isn't like the one like the perfect hand that everybody can plug into their robot and then just like start training off of. Because like all of the training data that has been collected till now is little Pinchy's.
It is like the people in the industry have discovered that this is a problem, and they're like trying to fabricate venture funded solutions, but I've not seen us anywhere close to a good solution for any of this yet, right? Like, it's the hands sort of exist. There's about 30 vendors in China that will sell you a hand, but we have no idea how to control them. The data collection for the hand is basically impossible. And if you think about it, it's really challenging. You have to retarget your own fingers to a different hand. Like, the hand's not the same as your same size as your hand. It's really challenging. Like, you can have all the doffs and tendons and like ropes you want. Don't even get me started about rope driven hands.
So let's say that like one of these does exist. You now have what? How many DOF is a hand?
22, I think.
Okay, so let's say that you have 25 DOF hands. What happens to the model? A model that already can barely take in force data.
So the solution appears to be, as the guys at Genesis are doing, to train a model that only does hands and ignore the rest of the robot. Like, if you look at have you seen the Genesis demos? The robot doesn't exhibit much in the term of like long range motion.
Correct.
It's entirely constrained to work on like tiny objects. Yeah, and that's how they're able to make it work.
But it doesn't solve occlusion. Right, occlusion, like you can't have a camera that's looking at all the fingers and also
occlusion is miserable.
But it's just let's ignore occlusion, which is not real. You can't do that. That is not how that works. But how does a model even take in 20 to 30 DOF of extra data, whereas right now it can barely handle force?
I'm like really curious whether inflating the output dimension makes the training slower. And if I only had some hand data, we could find out quickly. But we don't even have that right now. Like,
we don't have
it's
it
just it's honestly, like even after you do that, right? Like the hands need to have controlled amounts of friction in order to be able to hold up tools stably.
Let
You
alone
need to like handle tool slip.
we're not even talking about force sensors, right? Obviously, gel sites.
Man, no, yeah, the force sensors like quadruple the price of the hardware. It's so bad.
Gel site's terrible, but like, let's say that there's your 22 DOF plus what, force sensor per digit?
It's like 3, 4 sensors per digit, maybe more. I think is what
so
they're going at.
How does that blow up the training time?
It also has a lot of failure modes in the hardware. Like I don't know that hand would run for enough hours to collect a usable amount of data.
Yeah,
right? Like we're looking at like, I don't know, like the guys who are good are advertising like 1 million wiggles of the finger, which is not a lot of wiggles of the finger.
That's a unit right there.
Right?
What's the wiggle? It's just like this?
They don't specify. They just say like 1 million cycles between failures. But if you go look at it, 1 million cycles is not a lot. If you wiggle once a second, 1 million cycles is like a month of wiggling. It's very bad. And this is like state of the art too. The guys who can do 1 million cycles are like rub it in their face that their actuators are good for 1 million cycles.
Yeah.
I think the rope driven stuff is like still down in the like hours between failure. Like we can now operate for 300 hours before we need to retighten the ropes.
Yeah, they do get the compactness down, but
they are very pretty to look at. They just aren't pretty for very long.
I'm curious to see who is actually trying to, like, they acknowledge the video models exist, but they realize they can't just do video. Have you ever tried, like, your arm falls asleep for some reason, and then please pick up a coffee cup? You will burn yourself, right? You will spill it all over your body. You have all the visual data, but your model is trained off of force feedback. So suddenly your model doesn't have force feedback. It's got this like arm that's in static mode, and you're trying desperately to shove it into your face.
I guess the purely visual guys will argue that the robot will learn to look at the squishiness of the fingers or whatever.
At 240p. At 240p.
But it is, right. It seems to... using images as a proxy for force sensors seems like an inefficient use of pixels in a world where, as I said earlier, doubling the horizontal resolution of the image increases the runtime by a factor of 16.
Let's also mention that, like, do they even compensate for the aspect ratio of the images? No.
Latest training script...
You take a 16:9 and then you just tell it it's 4:3.
So I did check the latest training code base we were using, and it does in fact now pad the top and bottom of the image before resizing to 512 by 512.
Oh, it just adds garbage?
This code base was bad. It started by padding all of the videos to 1080p, then scaling the 1080p videos down to 512 by 512.
No!
But I think this was a bug. We're gonna pretend it's a bug and not a design choice.
The concept of the aspect ratio, who cares? That's crazy. That's
people.
Have you watched a movie with the wrong aspect? Like DLC's, like, I don't know what's happening. Here you go, 1-to-1, and it's just like you look at where.
Hey, you can't understand the video. Like, do you enjoy it? No.
No, do you enjoy it? No.
But the semantics are still there, right? But I do generally agree that aspect ratio is something that ML people are really slow to deal with. Like, it's usually about 1 year after the creation of a new field that they finally add like padding to the top to not squash the aspect ratio, and then like another 2 years before they learn to train a native aspect ratio.
Yeah.
Like, remember Stable Diffusion 1.5? The only supported resolution was 512 by 512. And like, the model didn't work if the image was rectangular. Like, even if at the same number of pixels, it like only understood square images. And it was like 2 years before we gained the ability to generate non-square images.
It was a dubious time.
It was a dark days.
So like, that's weird. Okay, so like the models have grown significantly in the last 2 years, right? We went from none of the stuff being useful to suddenly a visual model can almost do like a couple of hertz, right? Of feedback. That's 2 years. We have this call in 2 years from now. What the heck's different?
I'm really hoping that we start thinking about models that deploy on robots. I think this is a big gap right now, right? That the people who have the robots are not the people who do the models. You have, like, on one hand, like the good folks at Pi and NVIDIA who are like, just whatever, plug the robot into an H100. Everyone has one sitting around. But this is kind of a problem. Even
Yeah.
if the H100 were free, the idle power of the H100 is more than that of the machine, and it becomes like pretty impactful. Like even if the GPU was free and the electricity was free, you cannot have 700 watts coexisting with a person. It's like a significant impact to the well-being of the people in
Or
the
like
same
the
space
moment
as
you
it.
try to make that mobile, 700 watts is a lot.
It's a lot. It's like 1 hour requires a kilowatt hour of battery.
Yeah.
So then on the other hand, you have the guys like Hugging Face who are like, we acknowledge the model needs to be small, but the only robot we train on is like this toy plastic robot that we insist on 3D printing because I don't know, we're software people and 3D printing is the only manufacturing method we know.
Yeah.
Like, does it require 6 days to print the robot? Yes. Does it require hundreds of fasteners to build the robot? Yes. But it's okay because it's 3D printed and therefore easy. So I think there's like a deployment gap right now where like we need to pick a robot and like make it do shit. This is like really lacking. Like it's either big academic lab with a pair of robots mounted on a desk plugged in with an extension cord because batteries are hard. Or it's like, I have a toy plastic robot and I want to use it for whatever. I'm a high school student. This huge in-between gap of I have an $8,000 budget and I would like to purchase a robot and use it is something that I hope in 2 years we make a lot of progress on.
Yeah. I mean, okay. I love rooting for the underdog. There's the goofballs who are like GPU, and they're just desperately trying to shove this all into the largest FPGA you've ever seen.
Yes.
Some like Xilinx, just start waking up, or like who owns Xilinx now? Intel?
No, AMD.
AMD. Just wake up. Just start selling them at a loss. Just give me that good FPGA. I'd love this model to not consume 700 watts and instead consume 70. Right? Like
man.
Let's just pump the brakes. We are just some goofy analog FPGA that runs on magical chemicals, right? We get closer to that. Having an onboard compute that doesn't just chew up a kilowatt to sit still.
The biomimetism is a very interesting argument, and you hear it from time to time that brains are very power efficient.
Yeah.
Though I would argue that brains are terrible at data retrieval, and models are like pretty good at it. Like if I asked you to write me a long story about cheese, which is my usual prompt test these days, you would not be able to generate this long story about cheese at the rate of 50 words per second.
So that doesn't count. But like
a long story about beans.
There are some huge advantages to the existing like retrieval capability, which is great. But that's also not something that needs to occur in hyper real time, right? Like FPGA containing the model data. Right? Like just like we keep it in VRAM on a GPU, FPGA that locally keeps the model data, but has access to auxiliary information over a high-speed bus. Totally reasonable. Is it I think mechanically difficult as fuck to pull off? Yeah, that sucks.
A lot of people, I think, are like talking about variations of this. I think most of these companies are like, most of their goal is to raise funds and not ship a product, which is always really annoying. There's the folks from Etched. There's the folks from Etched who once gave a very specious argument surrounding like the area size of a FMA cell compared to the area of a GPU, arguing that we could just have 900 square millimeters of FMAs and completely ignoring the part where FMAs consume a lot of electricity. We could go fit like 55 petaflops into a die, but the resulting die would also be like many kilowatts. I mean, so like it would glow.
Is Jensen just going to rain down a 20x better GPU in 2 years?
No. Like there's no way to do this. Like it's like we're in the post-Dennard world, so we need to like figure out a solution to this problem.
Yeah, and like, do you think that there's going to be another DeepSeek moment where somebody comes out like, yeah, it turns out, and then like suddenly it's 10x?
DeepSeek wasn't really like a big moment. It was the first publicly disclosed like, look, guys, we can train an MOE. Like, contrary to what Meta tells you, MOEs are possible to train. In fact, they're really annoying to stabilize, but they figured it out. And the way you have to like look beyond the phenomenon that Chinese AI labs only do things that someone else has done before. Like it's like a repeatable pattern, right? And DeepSeek was finally the ones with the balls to do it first, which was interesting. But in the end, DeepSeek was a huge game changer for long context, because it turns out you can't have 1 million context at 400 billion active parameters. It's just like doesn't work. So, but it was more of like a not so much a step change as a stop sucking moment. Like
Yeah.
we knew it was possible. We just needed to stop sucking.
Well, there's still a lot of suck. Like to use the same metrics, there's still a lot of suck. Is there
robotics models are architecturally like big suck right now.
Yeah, they're like
almost no effort has been placed into the architecture.
The second you like slightly unzip, ooh, no, like that's yeah.
I think only some of the models recently have begun predicting across a horizon, but like this whole full attention across all of the previously seen frames to generate the actions is not going to work in the long run. The current physical memory of the model is a couple seconds because that's all the frames that can fit in context.
Yeah.
And I don't know what the plan is to solve this.
There's not. Like,
but I feel like we need a plan. Like, it's amazing we can get this far with only a 2-second horizon.
Yeah. I'm somewhat curious to see if solving that context issue gets us more hints as to how this is solved biologically. Right. We might get a hint as to how like context storage occurs in the person before we understand how, like, after we understand how it's actually functional long term in a machine.
It's the most cursed of questions that we're pretty sure humans don't use all-to-all attention to think, but all-to-all attention does appear to work very well.
Yes.
So, and humans in particular don't work that well. Like if you actually try to get repeatable output out of a person, it's difficult. It's very difficult to get repeatable, especially repeatable long context information out of a person. But maybe for robotics, it's a bit different, right? Like robots don't necessarily need to like output JSON with the commas all in the right spot. They just need to not smash your objects.
Are you advocating for non-deterministic outputs from robots? I love it.
I mean, it's what machine learning does. If you change the speed, you get a different answer.
Yeah, that's fair. But if you
no one's thought about this yet. Where the models don't work well enough that we have to worry about repeatability yet. Getting even the first shot to work is like hard. Like right now we do like. It worked 1 out of 5 times, so we put a footnote in the paper. It's top 5. Then we can show results that are 80% instead of 63%.
Yeah, it's gonna be interesting. Like I
just think about how bad it is, right? Like you ask the robot to go pick up like a cup, and the state of the art will miss the cup 1 out of every 15 tries. That's like really bad for a machine. Like if I tried to sell you a pick and place that missed the parts every 1 out of 15 tries, you would sue me.
The concept that this is like immediately pitched for elder care is wild. It's like,
my God,
yeah, I mean, I don't think you're gonna complain that much, and you're like, dude, that's.
I love how the elder care narrative is that the elders have low standards, so we can ship our equally mediocre robot. Right? Like, none of it is like the elders are like, we'll appreciate the robot. It's like we acknowledge the robot sucks. So we tried to find a use case where sucking was fine, and the answer was old people.
It's so goofy. It's so like, that's
about once a quarter, someone doing elder care shows up in my orbit, and I always like pity the elders that are being cared for by these foundation models. Like as a man who makes the foundation models and the data, I can tell you my expectations are low right now.
I'm totally for this large 6-axis old Kuka robot ripping garbage cans off the street and throwing them into a bin. But like, it will gladly do that to a grandpa. Like, just don't.
It's true.
Don't give these. We're not there yet, especially for that. Garbage.
Don't. It's so bad. They start with the number of old people in the world is increasing. Usually mutter something about Japan, which is famously full of old people.
Yeah.
Then the rest of the reasoning makes no sense. Like from the number of old people is increasing, they jump to it's hard to pay someone to take care of old people, followed by clearly the answer is emotional support robot. Like we started with grandpa needs to be like given his medicine once a week and quickly like leap over the wall to grandpa would love to like rant to a robot.
Okay, I got one for you. Do you think that if instead of training off of these like UR5s and robots that can't harm you, if we started with robots that could harm the researchers, that the models would be better? Right? If you were
right.
If you were like afraid to be around them, would you release a model as readily?
Like if the accidents were annoying, you would put in work to deal with the accidents.
Okay, so we're advocating here, to be clear, that the more dangerous the machine, the better the model that will come out of it.
Right. It's like how space grade code is so high quality, right? If the
Yeah.
rocket blows up, it's like a big problem.
I don't know, but this
So
robot's got to be like on their bench. Like I want the machine next to the researcher, and like
man,
you'd be. Dude, I would have so much more.
I think you'd quickly end the industry. Like we'd have no researchers left.
There's a happy impedance match. There's like the robot that can't kill but it can maim, and it's got to be like, oh man, I really shouldn't say.
Well, like the robot is squishy enough that he's impedance matched to the like stiffness of the joints.
There's a happy medium where like the output model is so much better because the researcher is so much like more afraid of the machine.
I haven't slapped myself with a modern QDD arm yet, and I don't intend to, but I imagine it's like somewhat painful. There was a famous video a few months ago of the guy kicking himself in the nuts with the Unitary G1. He made it. He was like he like recovered afterwards, I think. So that's sort of the limits. Like even with a pretty swift kick in the nuts.
Yeah.
But you do have a point there that the really small robots, like people just sort of ignore the failures because they're consequence free. They like shoot their YouTube video or their demo reel of the model succeeding. Because and we like carefully pick tasks too that are easy to reset after. Like there's, for example, very few teams, ourselves included, will go after soft perishables or like liquid perishables or spillables because it's so annoying to deal with mistakes. And I think that creates like a self-reinforcing loop, right? Pick and place is easy. If you miss, you try again.
Yeah.
And like you get the perception that it succeeded. But if like you actually went and completed tasks where failures had consequence, you would like quickly personally feel how your work wasn't up to scratch yet, and then maybe like, I don't know, put in the effort to become up to scratch.
It's fair.
It's like how the instant you give the LLM your wallet, you quickly discover that LLMs are not very good.
That's 100% accurate. The moment it's just like, oh, this actually has a huge impact on me. Like,
yeah, right. Or the moment OpenClaw deletes all of your files. Don't do that, kids. Don't do that, kids. Run it in a VM. Run it in a VM.
Yeah, very good.
All right. I think we've got it wraps here. This has been an exciting conversation, and I think we've touched on everything from industrial to like old people, senior care, we'll call it to be more correct. But it's an exciting field. We hope to have you back on again in the future, Dan.
I'm looking forward to what happens by next year.
Yeah. Honestly, six months. I hope to see some stuff out there doing something. Maybe you'll be the one. Maybe you'll be the first person to sell robot-generated canvases as NFTs.
There we go.